What's the hardest thing to measure in the universe? The answer will be distance. Figuring out the distance to the stars and the galaxies, I mean, you can't lay out a tape measure. You can't go there and drag with you a line to figure out how far away you are from your origin. How far away are the stars? How do you know? Well, they had to figure out a way to do that, and Hubble did so. You see, what happened was he found a certain type of star. They eventually became known as Cepheid variables. That's because these are stars that grow and diminish in their magnitude, their brightness, over time. Sometimes a very short period of time, sometimes a longer period of time. The reason they're called Cepheids is because the first ones were discovered as you look through the constellation Cepheus the House, which is right near the North Star, right near Polaris, okay, Cepheus. So they're called Cepheid variables. Okay, well, what happened was, through the work of Hubble and others, was they equated the brightness of these stars to their period of changing luminosity. So if they changed their luminosity over a short time frame, they weren't as bright. But if they changed their luminosity over long time frames, they were brighter. And they put them onto a scale of what they call absolute magnitude versus the period of luminosity. And all you needed to do, was find these Cepheids in other galaxies, measure their period of variability, and you'll know exactly how bright they are. Okay? Now, the reason this is helpful is because it's like this. If I have a 60-watt light bulb, and sometimes I'll illuminate a 60-watt light bulb in the classroom, you know exactly how bright it is. And if I put it right up to your face, it's quite blinding. But if I walk across the room, I can look at it, it's not quite as bright. That's because the light intensity diminishes over distance. Once again, another example of the inverse square law. The light diminishes in brightness according to the inverse square of the distance. Okay, now, if I know exactly how bright that 60-watt light bulb is from, let's say, 10 feet, and then I measure the light intensity from 100 or some other distance, some distance I don't know, but I measure the light intensity, I can use the intensity difference to determine how far away that light bulb actually is. Okay, easier to say, harder to do. And Hubble knew this. He knew that if he could get the absolute magnitude of a star in that galaxy, he would know how bright it actually is, compare it to how bright it appears to be, and that comparison will tell you how far away it is. This is brilliant stuff. They figured this stuff out. It's really remarkable. I always tell my students, you don't need to go to the stars because the stars come to us in the form of their light. We just had to be smart enough to figure out how to interpret that light. This is brilliant stuff. Okay, so Hubble had this distance calculator, and he determined how far away each of these galaxies were. And they were far different, far more distant than ever imagined. So in one decade, Hubble blew wide open the doors on this idea of the universe. The universe is far bigger than anybody imagined, and on top of that, it's moving, it's expanding. And on top of that, I now know what the stars are made of. Hubble should have won the Nobel Prize. But he didn't, because at the time, they didn't offer the Nobel Prize for astronomy. But he would have won hands down, because his contribution to science was enormous, perhaps more so than almost any other scientist of the 20th century. He revolutionized our understanding of the universe. Edwin Hubble. That's why they called it the Hubble Space Telescope. They got to name something after the guy, for Pete's sake. I mean, this was a major player in the game. Okay? So Hubble had figured out a way to calculate this. Now, the problem with his calculations of distance is this. He was wrong. He was wrong by almost a factor of 7. Okay? So something was, 7 million light years away. He thought it was 1 million light years away. But he was consistently wrong. So what happened was he still got his graph correct, where he plotted distance to the galaxy, to the velocity of the galaxy. The velocity came from how much redshift it was. So the more redshifted, the faster it was going. Okay. So when he plotted distance versus velocity, he found that there was a straight line as a result. That the closer galaxies were moving slower, and as you move further and further away, the velocity of the galaxies was higher and higher. This became known as Hubble's law. And that's been reformulated many, many times over the last several decades. And today we know that Hubble's law is 71.4 kilometers per second per megaparsec. Okay, I'll have to explain to you what a parsec is. So far you don't know, but I'll explain that in a subsequent video.